Welcome to Analog Integrated Circuits Design class. This is our lecture number 15. In the previous class, we discussed about folded cascode structure. So we'll continue discussion for some time, and then we will start differential amplifier. I'll give you an introduction about differential amplifier. So in the previous class, if you remember, we started with cascode amplifier. Um, we discussed about double cascode in the previous in lecture number 13, and we saw that if you extend the transistors in the stack, you can have many cascode structures, and this is one type, which is triple cascode. One important thing here to notice is whenever you have a structure like this, when you calculate the output impedance, the formula or the method what we use is the method or the formula what we have used for a common source with a degeneration resistance. So consider, so looking at this point, the resistance is R naught. Now when I see from this point, this impedance will be magnified by the intrinsic gain of M2. In a similar way, whatever seen from here will be magnified by the intrinsic impedance of M3. That is how we write the output impedance. The same thing will be followed even for the load structure, the PMOS devices. And then we saw the shielding property, and after that we saw about cascoding and versus increasing length, and we observed that in cascoding you will have the same overdrive requirement as in the case of a increased length structure, but output impedance wise cascoding is better. Then we saw the another improved version, another variant of cascode, which is called as folded cascode. The idea is instead of using both the input and cascode device, the same device type, we can have different devices by having a structure called as folded cascode, and we saw how these structures are drawn from the initial cascode structure, how you can fold the structure and fold the small signal current. So we also observe that whenever we go for folded cascoding, the output impedance seems to be lesser than the output impedance of a non-folded or a regular cascode, and biasing current requirement is also more in a folded cascode structure. So with that, we have concluded our yesterday's discussion. So today when we continue that, we will definitely come back and discuss about folded cascode when we start discussion on operational amplifiers in unit 2. But today we'll just see one more example or one more circuit where we can try to find the output impedance of such a structure. All right, so I'm just giving you a folded cascode structure. We know the regular folded cascode what we have seen in the last class. Say for example, if I'm starting with a PMOS input device, V in, PMOS input device, and this is the NMOS cascode for this, and we know that here we should consider or we should connect a current source I1. So in the previous class experiment, what we did is we have replaced even this I1 using a transistor. That is what we ideally, or that is what we do in practice. Now this is the output point, and from here usually we will connect, or in general we start with a resistive load. So I can actually keep a resistive load, but in order, if I do not want to compromise on the gain part or the output impedance part, what I do is I will replace even this using something like this, where this is a cascode load. So all these are maybe this I'll call it as VB2. Then I'll even replace this transistor also with a biasing structure VB1, VB3 and VB4. M1, this is M2, M3, M4 and M5. All right. So you will be wondering what I have done here by keeping these two transistors. So I'll talk about this after finding the voltage gain or the output impedance of this structure. So can you guys try to find the output impedance of this structure? Output impedance is the impedance seen at this output terminal, that will be equal to the impedance seen down in parallel to impedance seen up. Can I get answer for this question, what I have written here? The question is output impedance, R out. Any one of you, if you got answer, you can, all right, Yashita, you got the answer. It is GM2 R02. 1 second, let me read that. GM2 R02. Can you check again, Yashita, whether you missed any number, or you like whether the numbering of the transistors? You see, this device is M2 and this is M1. This is M3. R02. Alan, you are telling the final output impedance is R02, or yeah. All right, no issues, Alan. Yeah. So anyone else, if you got some answers, yeah, on the top side it is very good. Yes, GM4 R04 into R05. Yes, that is the resistance up. So what I'll do here is, we know that looking here at the drain of the PMOS transistor, being this node being at ground, this from here it is R05. Now the same resistance when I am seeing at the drain of M4, it is GM4 R04 into R05. That is impedance seen up. Now that will be in parallel with, so here what is the resistance seen here, which is R02. Resistance seen here is R01. Both are in parallel. So when that resistance seen from the drain of M3, it will be GM3 R03 into R01 parallel to R02. That is the output impedance. Yes, GM3 R03 into R01 parallel R02 in parallel to GM4 R04 into R05. Yes, I hope this is clear. So why I have taken this example is to check whether you guys understood how I have written the output impedance, or how to calculate the output impedance of such a structure. So if anyone in the class now, if you have doubt in writing the output impedance of this, please put, if you have a doubt, now you please put yes in the chat box. If there is a doubt in this, please put yes so that I can explain. So if this is clear, what we will do is we'll take a break from this discussion of folded cascode for the time being, because as I mentioned, we will revisit this folded cascode structure again in second unit when we start discussion on operational amplifiers. So we'll take a break for now, and we will start the next topic, which is differential amplifier. We'll come back to this folded cascode in unit 2. Also, when we start solving the numericals, what I told, I'll be sharing soon the question set. In the discussion of that also, we'll come back and see about cascode amplifier. There we'll definitely solve some numericals on cascode amplifier. All right, so I hope this is clear. In that case, we will start with the next topic, which is differential amplifiers. All right. So my one question to you is, so what comes to your mind when you hear about differential amplifier? So if you have some thoughts, or if you have some idea about differential amplifier, You can share now in the chat box. I just want to know what do you think about or what do you know about differential amplifiers. Op amps, very good, Avinash. Yes, it amplifies the difference of voltage. Yes, that is also true. Yeah, op amp. I think most of you are connecting this differential amplifier to op amp because op amp, whenever you learned about op amp only, you saw the circuit of a differential amplifier by providing inputs to an op amp, right? Yes. So what I want to point out here is whenever we talk about differential amplifier, we will all right. So we'll start like this. So let us understand what is a differential signal. So before that, let me write what is a single-ended signal. So what do you understand when I say a signal is single-ended? Let me draw a circuit diagram for your reference. This is our regular common source amplifier where you are providing input to the gate, you are taking output from the drain, and we know that both input and output are measured with respect to ground. So input is measured from gate with respect to ground and output is measured from source with respect to ground in this form. So this is plus minus V out and this is plus minus V. And this is how we measure voltages, right? So a single-ended signal means whenever we measure a voltage or single-ended signals are measured, voltage is measured with respect to a fixed potential. Single-ended signals are in general measured with respect to fixed voltage or fixed potential, right? So what do you mean by that? So in the circuit diagram where I have drawn this CS amplifier, you can see that output voltage is measured from drain with respect to ground, where ground is a fixed reference point. Similarly, you have input voltage connected to gate with respect to ground. Again, ground is a fixed reference point. So whenever we say single-ended signal or single-ended amplifiers, the meaning is the output or input or the signal itself is measured from a, from a node from an IC or from a node in a circuit with respect to a fixed reference point, and that fixed potential is always in most of the cases the reference point is it turns out as ground. That is a single-ended signal, and this is how or the single-ended signals are the signals what you have seen or what you have seen so far in almost all the circuits we discussed so far. Now let us see what is a differential signal. So do you guys have any idea what a differential signal is? We understood what is a single-ended signal. What do you think a differential signal will be? All right. Yeah, you guys think on that. It amplifies. Okay, that is the previous answer, I guess. Yeah. So a differential signal is basically measured between. Yeah. Yes, Avinash. I saw your answer. Both the terminal are varying. All right. Any other answers? Signal is measured with respect to other signal. Yes, that is right. Measured between 2 points, yes. Yeah, generally signals are measured between 2 points. One is a fixed point is what I told in the case of a single-ended signal. Now in differential signal, it is as you guys suggested or as you guys given in the chat box, differential signals are measured between 2 points, yes. But what is the specialty of those points? Those points are equal, those points will have equal and opposite signal excursion. Equal and opposite signal excursion. So what do you mean by this? Equal and opposite signal excursion. Let us see what is a differential signal. So say I have a source here, I have connected the source here, and I call this as a V signal 1 and with a specific impedance. Can consider that this is the source impedance Z, and I am considering one more source on the other side. I'll talk about impedance a little later. So as of now, yeah, another source in this side where this is V signal 2. All right. Now assume that these black boxes are impedance values. Now when I looked at the signal at this point, I saw that the signal at this point is in this fashion. All right. So if I measure the signal from here with respect to ground, I'm getting of this type, and we know that this is what we call it as single-ended signaling. Similarly, when I measured the signal, or when I observed the signal here, the signal is of this fashion, this type, and I can measure actually the signal from this node with respect to, say, I'll call this as node X and this as node Y. So I can measure Y with respect to ground. Again, that is a single-ended signal. Now, if we measure voltages between the points X and Y, right, if you measure voltages between points X and Y, where both the points X and Y have equal magnitude signals, but they are flowing in the opposite direction, the signal excursion is opposite. So such measurement, or when you do such as a measurement between 2 points where you have equal and opposite signal excursion, that signaling is called, or such signals are called as differential signals. Is that clear? So if I measure between, so plus here and minus here, or the other way, if I measure between X and Y either as plus minus or as minus plus, we call this as a differential signal. All right. So one more addition to this is whenever you say you are measuring between 2 points which have equal and opposite signal excursion, and if you want to call that as differential signal, in most cases or in general, the impedance also should remain same. So these two impedance also should remain same. That is one more additional condition. So it should also have equal impedance. Are you guys with me? Are you guys following?
Yes, sir.
All right. Yeah. Fine. So in such cases, what we will say is, since the signals are equal in magnitude and opposite in direction, we call the signals as anti-symmetric signals. Signals are anti-symmetric. All right. Fine. So any questions on this? Yes, that is very important. VXY, very good. Whenever you go for differential signaling, okay, let me explain that. Whatever Avinash has written, I'll explain it now. Say for example, um, 1 second. Yeah. Okay, so I'll explain that. Yes, Avinash, Vxy is twice, that is right. Uh, say for example, at node X, so in the previous circuit at node X, you have a signal, you have a, say you have a sine wave, maybe I'll write it as V peak cos omega t plus, okay, so one more thing you need to understand here, where the signals here are swinging on a DC voltage, and this DC voltage we generally mark it as VCM. What is, and this the DC voltage on which the signals are swinging, we call it as common mode voltage. This VCM are called as common mode voltage, right? So let us assume that at node X the voltage is Vp cos omega t plus VCM, and at node Y you have a specific voltage which is minus Vp cos omega t plus VCM, right? What is the meaning of that? VCM is the DC voltage on which the signals are swinging. All right. Now, when you write the peak to peak voltage, so when you measure the differential signal at x with respect to y, if I measure, how will I measure? I'll measure Vxy as Vx minus Vy. Right, Vxy is I'm measuring at x with respect to y, so I can call it as Vxy. And what is Vxy? Vxy is Vx minus Vy. So how will I write that? It is Vp cos omega t plus Vcm minus Vp cos omega t minus Vcm, or this is equal to 2 Vp cos omega t. All right. So whenever you measure it as a differential signal, the peak voltage is or the voltage is actually getting twice. All right. So Vp is the peak voltage. So that is basically getting twice than the previous. All right. Or you can understand in another way also. Okay, I hope this is fine. So what I marked here is with respect to the peak voltage, so the peak has become twice. Now yeah, so the peak to peak will be equal to 4 times of that. So one more thing to note here, whenever you talk about a differential amplifier, sometimes, since your output voltage is because you are measuring between 2 points which is having equal and opposite signal excursion, your output will be twice of that of the single ended, and in certain cases even this will go beyond the power supply, because you are not measuring with respect to ground, you are measuring with respect to two different points have equal and opposite signal excursion. All right, so is this clear? Any questions on this? All right. If you have questions, please keep me posted here. I'll respond to that. Now you will be wondering why we all of a sudden we are shifting or we are moving our focus towards something called as this differential amplifier. So let me tell that. So let us see what are the advantages if I use something called as this differential amplifier. So can I guess what can be the advantages if you have differential amplifier? One thing we saw that you will get actually a voltage swing more than a single ended. That is the inherent thing which is coming as you are measuring differentially. Apart from that, what do you think? What other advantages this will have? Any clue? Yes, more immune to common mode noise. That is very true, Bhuvan. Yes, it is more immune to common mode noise. Or one thing I forgot to mention here is your signals were actually swinging on VCM, as this as Vp cos omega and this is minus Vp. So when you measured, the common mode voltage is actually yeah, because the DC voltage is basically when you measure the voltage, it is actually going to a zero level, right? Because your VCM and VCM is actually getting cancelled. All right. Yeah. So let us see how it will reduce the noise in the common mode signal. Yeah, so let me just list out the advantages. We are specifically looking at two advantages. One is it is immune, to noise or common mode signals. Immune to noise or common mode signals. And the second advantage is it is also immune to power supply variations as well. We'll see in detail what are these two, because understanding of this is very important. Otherwise you will always have a question in your mind, why are we going for this differential signaling? All right, so for this we will consider one simple example. Say you have an amplifier here. So assume that this is an amplifier in an IC at one point of an IC where you have a signal like this. So whenever you have a signal of that fashion here at the output, it will be opposite, because we know that there is a phase shift from gate to drain, or that is why we have always written the gain expression for a common source amplifier as minus GM into RD. I hope that is clear. Now say I need to connect this node from this point of an IC to a faraway point. Say I need to stretch this through some metal line and take this to some other end of the IC. All right. Now yeah, so at this end, definitely the signal at this point is amplified signal, and that amplified signal, if I look at this point, so I have taken that signal from that end to this end, and I'm just magnifying that to show that this is amplified, and this is the signal what I have here. All right. Now, so when you look at an IC, when you look into an IC, there will be many components. If it is a complicated IC, when I say when there are many number of circuits there, you will have analog circuits on one side, you will have some other digital circuitry somewhere other side. So whenever you take a signal from this amplifier and you are taking to some other point, very close to this, there may be some other signals also moving, right? So I'm considering one such example. Now what I'm telling is very close to this metal line. So why I'm calling this as metal line is, if I want to take a signal from one point to another line, I need to use conductors. That is why I'm calling this as a metal line. So this is acting as a conductor. Now very close to this metal line, I am seeing uh, one more metal line flowing, going like this to some other point. And when I looked at that metal line, what I saw is that metal line is actually carrying a signal from an inverter. All right. So basically this is a clock signal. I have a clock signal, and through an inverter, that clock signal is also taken to some other point. Right. So what I will have here is also a signal. Let me just use a different color here. So what I have here is a clock signal. This is for some other need in the same IC. Hope you guys are with me. Are you guys with me? If yes, please put an S in the chat box. All right. Okay. Now, now see what I. So similarly, I am considering one more uh, circuit here. Considering one more circuit here. Let me talk about that little later. Now, see that you have this as one metal line, and this is the first metal line, and this is the second metal line. What I have here, and both the metal lines are actually carrying a signal. Right. Now these two metal lines are inside an IC, and what is there between the metal line, what you can assume is there is a substrate. It is a substrate which is not having any conducting substrate is not a conductor as such. The metal lines are actually conducting. So what you can assume is there are two metal lines carrying signal. In between, it looks like an insulator type. So we can think of numerous capacitors in between. We can think about so many capacitors. So when I talk about capacity, it's not like physical capacitors we are adding there, but the capacitive action because of two metals separated by distance where there is no conduction, or the conduction is very less. All right, because there is no signal flow exactly between these two metal lines because of the substrate in between. I hope this is clear. Now, what we will see here is the metal lines is basically carrying a clock, high frequency clock, which is changing rapidly to up and down, right? So when you look at this line, this line is carrying a signal which is changing to high and then low, then again high and low, and this action is very rapid because that is a high frequency clock. I'm thinking of such a situation in an IC. Now, when this metal line is changing its signal voltages from low to high and high to low, since you have capacitors here, these changes will be directly coupled from this line to the next line. And what it exactly look like is the when there is a change from this low to high, when there is a change from this low to high, the capacitor will also reflect the same change, and as a result you can see a small spike in the signal here, because this spike is coming to this metal line through the capacitor, because down metal line there is a sudden change in the signal, and this is reflected at all the points of this signal. I hope you understand this what I am trying to say. As your signal in the lower metal line is changing, the capacitor is bypassing, or capacitor is giving the same change directly to the top, and spikes are appearing on the signal there. Right. Now the same thing is the same thing holds good when if you have another line here which is also carrying a signal, and you can again think of numerous capacitors connected between these lines, which will uh, actually give the changes happening on this line to the other line, and say the signal here is of this fashion, so the output it is of the opposite phase. If I look at the signal here as such, it will flow in this fashion, right? Now, when there is a change from low to high, the same change will be reflected on here, then on here, then somewhere here, then somewhere here, like this. All right. So, what I'm trying to say here is there are two metal. So, this is your third metal line. Right. So, since there is a high frequency clock flowing through the second metal line, the changes in that metal is coupled to the top and the bottom line in the form of spikes. And if you see the waveform here, let me call this as Vx and this as Vy. If I look at the waveform at Vx and Vy, and if I am doing measurement with respect to ground, I will retain all these spikes in the signal. Right. But what is the advantage of a differential signaling? When I go for differential signaling, what I will do is I will measure this with respect to this. So when I measure the signal at Vx with respect to Vy, I'll get signal as double, but what happens to the spikes? The spikes will get cancelled, or spikes are formed as a result of the noise which is coming from the second metal line to the first as well as to the third metal line. And the spikes or the common mode signals, or the noise from the common mode signal, or the noise signals will disappear when you go for differential signaling, but at the same time your signal will get double. Is this concept clear? Can I get a response in the chat box? If you have any questions, you can please ask now. All right. So this is why, or this is how we say that differential signaling are immune to noise, right? So you can think of the spikes which is coming on the top and the bottom signal as noise from the high frequency clock which is taken through the second metal line, and those noises can be definitely removed by going for a differential signaling. All right, Avinash. Yes, that's a good question. Uh, so you have a high frequency clock in the second metal line. So the capacitors are coupling the changes from that metal line to the first line as well as the third line. If the lines are closer, and those changes will be appearing in the same direction, right? When you have a pulse going up, the change is up actually. So there will be an up spike. When the signal is going down, there will be a down spike. So that spikes will be reflecting on both the signals, or any number of signals which is coming close to this metal line. And now how is it get cancelled? You can see that, say for example, I'm marking it as value of plus A. The spike value is plus A. Here also it is plus A. Now when I take the difference, so when I say differential signaling, I will do Vx minus Vy. You can see that the signal here, say for example, this is of value -1 and this is a value +1. This is a value +1 and this is of value -1. So when I do -1 minus 1 value here, it will go to -2. But at the same time, when I do this the subtraction, what I am doing is a minus a, which is equal to 0. All right. So I'll come back to yeah. So let me check with Avinash. Avinash, are you clear? How the noise are getting cancelled? All right. Yes. Amitesh, are you clear how the spikes are appearing on the third line? It is as same as how it is appearing on the first line. All right. Now you had asked one more question. Do these spikes cause distortion? So generally we say a distortion is when there is a change of shape of the waveform, or whenever the shape is not preserved, we say that it is a distortion. But what you can see here is the signal, the sinusoidal variation is there, and upon that you have a spike. So when you do proper differential signaling, if you are able to reduce, if the spikes are getting cancelled, the signal will not be distorted at all. All right. Yes. Fine. So this is what we need to understand when you talk about differential amplifier. It is immune to common mode signal. In a similar way, it is immune even to the power supply variations. Say for example, I am doing in this way. So I have a signal. I have a circuit of this form here. I have a circuit of this form here. So as as we told before, we'll be providing V in here, and this will be minus V in, and we are going to measure between these 2 points. Now, when we talk about power supply variations, what I meant is, so what we are expecting from this DC power supply is this VDD should be constant. Now, there are cases we can see that this DC supply voltage or VDD what we are expecting will not be constant. This may, there will be some variations in the power supply. It can reduce, it can decrease, or it can go high, or even there can be variations or small fluctuations in the supply voltage. Now, whenever you have supply voltage fluctuations, that fluctuations will be affecting this path and this path in the form of current fluctuations, and as a result, you will have fluctuations in the DC voltage developed here, right? Now, when you say differential signaling, as you are measuring between these 2 points, even those fluctuations, it will appear at this point equally, such that when you take difference, those fluctuations will be completely cancelled out. I hope that is clear. That is what power supply variations. It will affect both the points equally, and those effects will be completely cancelled. Yes, Akash, I think you have a question. If impedance matching and line transfer characteristics affect, can you give a little more clarity on that, Akash? In what aspect you are asking? Impedance matching of what? Transfer chara like conductance. No, you're asking with for the previous this discussion of this discussion is what. Oh, okay, all right. Now here actually, see, we talk about impedance matching and other stuff only when we work at higher frequency. When if you're working on a higher frequency, yes, we need to talk about impedance matching. But generally for analog circuits, we rarely talk about impedance matching for several reasons. Now, I'm trying to understand your question, because your question is, will impedance matching and line transfer chara affect? Probably Akash, you can unmute and ask the question.
Sir, the impedance matching in the output where we are checking, and
Okay.
the input where we are supplying.
Okay.
So will there should be an impedance matching between those two.
Those two means if you look at this circuit diagram, you are talking about this point and this point.
Yes, sir. Yes, sir.
That is a simple metal line, right?
Okay, but those will that metal line won't have any losses or something?
Yeah, so that is true when you talk about something outside an IC, because the distance between these two metal lines is very less, right? Because when you talk about an IC, altogether IC will be of in the form of a some millimeter square area, right?
Okay, is it inside the IC?
Yeah, I was talking about something inside the IC, not as a transmission line. I hope you were referring to such kind of stuff.
Yeah, yeah. Yeah.
All right, yes, Akash.
Thank you, sir.
Yeah. All right. So I don't know whether I elaborated this so much about differential amplifier and the advantage by like the advantage of differential amplifier with respect to noise rejection and supply voltage variation. But this is very important to understand. So what we will do now is we'll quickly see how we can develop the topology of a differential amplifier, because I want to say that this is not a differential amplifier circuit is. It is not like bringing two CS amplifiers together to get a differential amplifier. There is a careful thought process behind developing a differential amplifier. All right, so we'll quickly see that. This is very interesting how we will develop differential amplifier circuit. We'll just kickstart that and we will continue that in the next class. All right. So if you ask me the definition of a differential amplifier, I would say what we need as a differential amplifier is a high gain amplifier, because everywhere we need high gain amplifiers. All right. Now one more need is it should be a high gain amplifier, and that amplifier circuit also should respond to a differential signal. So the circuit should respond to a differential signal. All right. So we understood what a differential signal is. Now we are looking at a circuit which can amplify such a differential signal. So I have written two requirements. One is it should be a high gain amplifier, and the second is it should be a circuit which can respond to a differential signal. Now, going back and thinking about the configurations what we studied so far, we have a common source topology, we have a common drain topology, and we have a common gate. These are the three basic configurations what we have studied so far. Now, out of these three configurations, which configuration do you think, or which all configurations do you think are suitable for this differential amplifier? Can I get your answers in the chat box? We know about three configurations: CG, CS, and CD. All right. Yeah, Akash, you believe CG is a good option. Ayushi, yes, your answer is either CS or CG. Yes. Any other options? CS, CG. Yes. Most likely we will go for CS and CG because both have some gain. But in case of CD, we know that CD is not at all an option because CD provides unity gain, right? Less gain. Now, then we have CS and CG. Yes, of course, CS is a suitable candidate. Now, coming to CG, we can use CG, but there is a problem with CG amplifier. The problem is the input impedance of the CG amplifier is very low. Because if you remember, when we spoke about the input impedance, in common source and common drain, we never spoke about input impedance because input is directly given to gate, which is providing a very high input impedance. But in the case of common gate, the input impedance was very low. It is approximately equal to 1 by GM. So if we are using CG, we have to take additional care to see that the input impedance is boosted. But as of now, we have no, or we are not looking at that option as of now. The only thing we need is a circuit which can provide high gain, which can also provide a respond to differential signal with high input impedance. All right. So with that in mind, let me go for a circuit, the CS amplifier circuit, because that is a suitable candidate for this. Now this is R and this is V naught, and this is the point V in. All right. Now this V in is actually measured between gate and source, or that is VGS basically, and I'll write VGS as VG minus VS, where VG is V in and VS is 0. Right. Now, how will I write V naught in this case? V naught is equal to minus GMR into VGS, right? Minus GMR into VGS, or I will write minus GMR into V in minus 0. So why am I writing in this fashion? Because what I can say here is this node will provide an output voltage, and that output voltage is basically the difference between the gate and source terminal. So uh, the the output of the CS amplifier is minus GMR into difference between the voltages connected to the gate and source terminal. All right. So let me look at this way, the same circuit. Say this is V in 1 and this is V in 2. What is V out? So how can I write what is V out in this case? So there are two signals, right? So so this is our basic idea. This we already know. What I'm trying to do here is I have just taken the same circuit, and instead of connecting this to ground, I am just marking it as V in 2. Now, how will I write the gain of a circuit when there are two inputs? When there are two inputs, generally what we do is we short one. Yes, Vaishnavi, yes, Akash, I saw your answers. That is right. But I'm trying to give you a slightly different picture. So, what I will do is when I have two circuits, first what I will do is I'll keep the first circuit here, V in 1, and I will ground the other circuit. This is the equivalent for V in 1. Now, what is the equivalent for V in 2? This is V in 2, and this need to be grounded. This is the equivalent for V in 2. Right. So, if you think of the CS amplifier, even the CS amplifier, if I suitably modified, I can say that this will respond to a differential signal because the output at the drain is basically the amplified or the magnified version of the difference between the voltages at gate and source. So as you guys suggested, I can say V out is equal to minus GM into R into V in 1 minus V in 2. That is true. But can you tell me, there is one problem here, the same problem what we discussed as before. What is the problem here? For V in 1, input is actually seeing an infinite impedance, that is fine, perfectly fine. But for V in 2, the input is not seeing a high impedance, it is seeing a very low impedance. Right. The input signal at source is actually seeing a low impedance. Now my question is, do you guys agree to that? If I'm connecting two different voltages, one at gate and one at source, gate will see a high input impedance, but at the source it will see a very low impedance. Do you agree to that? Do you understand what did I say now? All right. So what we can do, I need to fix this problem. The problem is of low input impedance and I need to fix it. So how will I fix it? I'll keep the same circuit here. At gate, I have no issue. Gate, I can directly connect a signal which is called as V in 1. But at drain, I cannot directly connect the signal because the impedance seen from here is very, very low. Now, if the impedance seen is low and I need, yes, Akash, one more MOSFET. Yes, we have to put one more MOSFET, but how we have to put is what my question is. Now, see observe very carefully. What I need from here is I need to see a very high input impedance to connect this V in 2. But the impedance seen is very, very low, which is close to 1 by GM. Now I need to provide a high input impedance for the V into source without changing without disturbing the signal. So how can I do that? Are you guys getting my question? The signal source should see a high impedance, but the signal should come as such. Signal should not be modified or it should not be amplified. So what structure can be used when you want to connect a high impedance to a low impedance? Buffer, yes, buffer, yeah, CD, that is very true. So what I will do here is, since I am seeing a very low impedance towards this side, I will add a stage here and I'll provide V in 2 here. What is this stage? This stage is a CD amplifier, which is basically a buffer. We know that the input impedance is same as infinity. So my previous requirement of V into seeing a high input impedance is satisfied. At the same time, since CD amplifier ideally give a gain of 1, the same V into is available to this point also. Is that clear? I think one of you have unmuted. Please kindly keep in mute. Yeah, thank you. Yeah, so I'll wind up this soon. I'll just build the rest of things. So how can I configure a CD amplifier here? What is a CD amplifier? CD amplifier is whenever you have a MOSFET and if I connect in this form, V in, and if I take output from here as V out with a constant current here, this is a CD stage. Right. So plugging in the same series stage here, what I can draw here is, this is my initial transistor where I have connected V in 1. Now to this point, I need to connect a CD amplifier here, let's say with a constant current I. This is I. Now this is V in 2. So at this point you will get V into buffered and that will go to this. And if I take output from this point, I can say this is equal to minus GMR into V in 1 minus V in 2. Is this clear what I have written here? Is this clear what I told or what I have written here now? What about rest of the class? So I did not do anything. The same first expression is kept here, but the only change what I have made is instead of connecting V into directly to the source, yes, Amitesh, I'll come back. So instead of directly, yeah, see the expression remains same here. There is no change to this expression. Only one thing I did. What I did, instead of connecting V into directly to source, I have connected V into to the input of a CD amplifier and I replaced that circuit diagram over here. This is V into and this is the output of the CD amplifier which is giving this V out is equal to V into buffered. So if I assume that the gain is 1, the V into is same as V into buffered. Alright. So I just added the CD amplifier. So previously I wanted to give V into directly here, but that V into is now shifted to this point. But that did not change anything else in the circuit. Is that clear? Okay. So what is a CD amplifier? What is basically a CD amplifier? Generally you will put a resistance here, but we know that resistance will be replaced using a suitable current source, and current source in general we will replace using a transistor. It is as same as how we started a CS amplifier, right? Started with a resistive load and later we said that we will not keep resistive load because of the higher value of resistors, and generally that will be replaced using, ideally what we need is a current source, but that current source will be replaced by a MOSFET. It is, you can think that as a load of the circuit. When you have a current source, the load resistance is infinity. When you have a resistance, the load resistance is R. That's it. Okay, one more addition to this. Now, if at all, if you know this voltage is minus GMR into V in 1 minus V in 2, say if I am connecting a resistance here, if I am connecting a resistance here in this fashion, and if I take output from this point, can you tell me what will be the voltage available at this point if both resistance are same as R? This will be simply minus GMR into this voltage V in 2 minus V in 1, which is buffered. Because if I look at this point, V in 2 is directly to the gate of this transistor, but V in 1 is coming from the previous transistor but through the source. So for this transistor, actually this is the signal coming in from here, so this is acting actually as a common drain. Or I can draw the structure in common like this. By just pushing the current source to the middle of the circuit. This is V in 1 and this is V in 2, and at this point I have minus GMR into V in 1 minus V in 2. At this point I have it as minus GMR into V in 2 minus V in 1, or this can be further written as GMR into V in 1 minus V in 2. So if I look at this voltage and this voltage, and if I measure between these 2 points, it is as same as a differential amplifier. So if I take voltage between these 2 points, this is a differential amplifier. Is this clear? I can take either plus minus like this, or I can take plus minus plus like this. Is this fine? All right. So we'll continue the discussion of this in the next class. If you have any doubts, I'll explain it more during next class. So as of now, I'm just winding up. Thank you so much for joining. We'll continue in the next class.